The original robot that was the inspiration was based off of two new nets made of silicone rubber with 3D printed end caps. The end caps included kirigami claws to provide directional adhesion. Unfortunately, this design, while effective, required several manufacturing process steps and 2 days to complete. All items can be found on Amazon.ca or your local grocery store. High and low density polyethylene tips were used for interconnections, vacuum bags were used for the pouches, impulse sealers for assembly, and other materials such as packages from the grocery store can be repurposed to make these inexpensive soft robots. The total bill of materials is only about 40 cents Canadian for the robot and $35 for assembly. Here we can see the parts of the robot prior to the assembly process. We have low-density polyethylene glue tips, a syringe, silicone rubber tubing for connections, the vacuum pouch, and a rotary blade for cutting materials. The rotary blade can cut the glue tips very precisely to smaller sizes so that they were adequately sticking to the silicone rubber tubes that we use in later parts of the process. For this example, we're taking the polyethylene polyamide layer and taping it to a piece of polyester with the polyethylene side up. This allows us to take the small polyethylene tubes and bond them directly to the sheet in a later step. We're aligning it in this case to a template, which may or may not be necessary, but is useful in this work so we can ensure that we get approximately the correct centering of the polyethylene tubes. To bond the polyethylene tubes, we've preheated a hot plate to approximately 145 degrees Celsius. We can then align the pre-cut polyethylene tubes and bond them to the polyethylene sheet with only a few seconds at a light pressure. Once this is done, we can then remove the entire sheet and let it cool down. The process takes only a few seconds, and it gives us a very strong, reliable bond. Once these sheets have cooled to room temperature, we can then perforate the sheet using a needle or a wire. This allows us to provide the interconnection between the tubes and the rest of the pouch that will be assembled at a later step. Although the sheets can come out fairly warped to a start, once they are welded together with an impulse sealer, they remain flat and very functional. The impulse sealing process itself is shown here at double speed. It's quite effective at reliably bonding the polyamide layers. This is important because we are keeping the polyethylene layers on the outside of this actuator so that we can connect them to other parts of the soft robot. You might have to change the temperatures and the time settings for these impulse sealers to ensure appropriate connection. Generally speaking, the polyamide requires a higher temperature and/or time to ensure adequate sealing. In this case, we can also use the impulse sealer to seal the polyethylene pouch directly to a high-density polyethylene sheet, recovered in this case from a milk jug. It's entirely possible to have these sheets bond instantaneously and extremely strongly to the high-density polyethylene because of the material compatibility. If we want to have parts of this plastic soft robot be changed like an origami, we simply have to use the impulse sealer to soften the corners and then bend the material until it cools. This allows us to make these sheets that are normally flat into folded structures, and it can work easily for both high-density polyethylene as well as the PET layers that you might find from packaging materials. Now, the kirigami claws can be manufactured either with an X-Acto blade or scissors, but in this example we're demonstrating how they can be designed within Silhouette Cameo Craft Cutter's tool. They introduce a folding zone as well as a serrated cutted edge, so that will become the kirigami claw itself. Additionally, we are introducing two tabs for this structure to be folded in and connected to each other without aid of glue or tape. This demonstration of the folding of a kirigami claw is done with a two-sided plastic. We can see that it's a very simple matter to push the slots through, and then the serrated edge is then protruding past the bottom of the remainder of the claw. A more complex design of a soft robotic system is actually shown here, made from a single piece of overhead transparency. Both the base of the system, the kirigami claws, arms for the actual robot to extend past the main body, and a folded body that will be part of the main core actuator is demonstrated in a single process. Unfortunately, while this design was elegant and simple to manufacture, it was not strong enough or rigid enough to work as a soft robot for the crawling test. As a result, we had to modify this design to work with high-density polyethylene sheets, which were heavier in general and provided a better center of gravity for the actual soft robot shown in the following demonstration. After successive tests, we were able to get this primarily high-density polyethylene robot working. It had kirigami claws made of PET, and both the actual antagonistic actuators in the middle of the robot were made of the vacuum bags. Surprisingly, we actually had to add extra HDPE to this robot to make it heavy enough to enhance friction. Further optimization is of course possible, but it's pretty good for only a few cents worth of material. While not completed in time for this project, we've also investigated different actuation mechanisms using the same vacuum pouch. In this case, an antagonistic actuator can be slipped over top of a different piece of polymer without having to have any bonding integration to begin with. As we demonstrated in this case right here, we can change the curvature of a simple piece of plastic simply by slipping the curving actuator over top. This bending can be amplified by using the hair clip mechanism developed by Zichen Jiang and co-authors last year and presented at ICRA 2023. When we do this, we get much greater ranges of motion with a very simple antagonistic actuation in the middle. Well, we'd like to thank the organizers at Robosoft 2024 for giving us the opportunity to present this work. This video was done by the Impact Lab, but it couldn't have been done without the amazing contributions of many of my undergraduate and graduate students, including Xiaoqi Ma, Portia Rayner, Luca Marita, and Xiaoru Sun. Thanks again for your attention. We hope to see you in person at Robosoft 2025.